Welcome to Autodesk PartMaker SwissCAM 2023. Today we will be looking at programming this bolt. We'll start by importing the solid model. From there we establish the machine coordinates, the zero position of the part in the guide bushing on the main spindle. From there we will take the 3D profile and extract 2D geometry, and then from there we can program the 2D geometry. So the first thing we need to do is to import the solid model. Under PartMaker's import function, we can import 2D wireframe models. We can also import 3D models, neutral files, X_T, X_B, SolidWorks part files, SolidWorks configuration files, Autodesk Inventor files, STL models, Pro-E files, and step files. Once the model's imported, we'll use the Edit Part Coordinate System to set the origin to the front of the part for programming purposes. You'll select the part, select the method of setting the origin, in this case, arc circle center. I just find an arc on the face of the part. I set that value, and if I need to rotate my coordinates to have Z facing away from the part, I can rotate my coordinates with the rotate function here. In this case, we're good to go. We don't need to rotate anything. I'll just close the window, and now we have the part oriented for programming. Next, we go to the setup dialog box. In here is where you'll tell the system whether you're working on the main or the sub spindle. Then you will determine your machining functions, turning windows, milling windows. We have a mill cylinder window here so that we can wrap features around the part. I'm using multiple ZY planes. The reason for this is so that I can time these features together. Then we'll do some sub-spindle work and some end polar work to create the back end of the part on the sub side. Below, you'll notice that we have the length of the part, the diameter of the stock we're using, the excess stock, which is how much I'm facing off the front of the part. PartMaker wants to know the exact amount of stock you're using. So if you're facing, we need to know how much you're facing. That way we can create parts that are equal length all the way down through the bar. The guide bushing length here is the support area of the guide bushing. So any tool paths that are longer than this length here can be problematic, especially if we have to draw the bar back and forward in the machine to create the milling features onto that part. So my strategy today will be using multiple turning operations so I can break up the turn and the milling features and then recombine them or reorder the operations so we can safely create the part moving down the bar. The guide bushing diameter, this value needs to be greater than the OD of the stock. This diameter value here is actually for simulation purposes. So you can make this any diameter you want other than the stock OD. It just has to be greater than that. So we've created a main turn window. That's the first window I'm going to work in. Apply and close. And from here, I extracted my turn geometry. And now I can work in the 2D frame or on the model itself. In this case, when I'm planning turning, I like to work off of the 2D plane. It just makes things easier for me when I'm programming the length of my turns. So the first operation is the facing operation. It's a contour strategy. The tool location is on the face of the part. From here, I just select a tool. Once my tool is loaded, I can look at my tool, edit it if I need to, change what I need to change in here. Select OK, apply and close, and the facing operation is automatic. We've established the origin of the part and we've established the size of the stock, so the system knows where to start the tool path and where to finish it with a facing operation. We can establish a 2D profile and run the tool path itself, and we can also do that in the 3D window. The 3D window is going to give us a little more control. We can show the motion of the part instead of the tool motion in the 2D window. We can show a sectional guide bushing, and we can show the tool path. and we can step it through if we need to. So there's the sectional guide bushing. Here's the part inside the guide bushing. If I want to, I could actually show shadow stock. So you can see the stock in the guide bushing as well, and then step the part through. And we're done with the facing operation. So one of the strategies that I like to use in PartMaker is to create all the turning strategies needed for the part. This is not the order of operations. This is just a series of features that we're building to create the part. We will reorder these operations inside the process table when we generate it. So for now, all we need to do is create the features on the part, any order that you want to. So I'm doing a first turn here. Follow that up with a second turn. Again, I'm trying to make sure that my tool pads are not greater than the length of the guide bushing. Until I can get into an area where I know I don't need to draw the bar back, then I can start making longer turns. I can also put the machine into support function if I wanted to do a long turn and use a sub spindle to support the part. I'll be doing that for the back end here. So then we build the grooving strategies. This is the small groove. This is a larger groove. Again, building the tools I need for the strategy. In this case, I'm using a full nose radius for this particular feature here. Next, drilling the hole. I'm just spotting, and then I'm going to use a PEX cycle to clear out the long hole here. I am using a custom drill shape just due to the fact that there's an odd angle on the back side of the part here. So I just had to drill ground to that same angle, and we're going to use that to punch the hole into the part. Then the third turn, the fourth turn, and the cutoff. So that takes care of the turning strategy. Next, we need to deal with the milling strategies. We've got cross holes, centered holes. We've got a small feature here. So we need to remove material between these bosses. We have a large slot here with a couple different depths to it, and the sprocket work on the backside of the part. So by using the predefined construction planes, in this case, I'm going to start with a mill ZY plane that I have indexed to 120 degrees. So let's pick that window. View normal to the face plane. I'm now looking down on the part. I can now machine it. So my strategy in this case was just to punch a drill through and then use a ball mill so that I can create these tabs at the bottom here. And I'll just go ahead and plot that. There we go. Then I started timing the features together. The next window that I went to was a mill ZY window that I had indexed at 30 degrees. The mill ZY plane is perfect for working around the part, especially when you need to time features. And you can get the information from the model itself. We can interrogate our model for information if we need to. The strategy that I'm using here is just a simple little strategy so that I can create the fillets. I'm using a 156 tool. And again, all I'm doing is putting in the edge break that they wanted on the part. Next, we'll go to the next construction plane. In this case, I'm putting this hole in. And then from there, I'm just working my way around the part, finding the geometry that I need to gather information from to create the feature. The mill cylinder option here, what I'm doing here was I created a single tool path, and then I copied the tool path around the part using the mill cylinder function so I can keep my tool coincident with the edges here. Let's put in a small delay here. And I'm going to turn off the stock verification just so that we can watch the tool work. As you can see, I'm just going around the part, clearing out the area between the bosses. From there, I broke up the slot function again. I created a front side, then a back side, then the deep center slot. And again, I'm breaking this up so that I can turn, mill, turn, mill, turn, mill, keeping the bar inside the guide bushing. So that took care of the main spindle. Next, we go back to the setup dialog box. I tell the system I want a new sub-spindle turning window. PartMaker will automatically flip the part around so that we can do our ID work on the sub side. And in this case, it was just a matter of punching in that small hole there. Roughing out the sub side, and then doing an ID bore. From there, I wanted to work on these sprockets using Z-oriented tools. So I created a sub-end polar window. From there, I created the tool path for the sprockets. And in this case, I'm using multiple Z-level steps that you do not see in the 2D window, but you will see in the 3D window. So if I ran this in 3D, you'll see that I'm using a step-down technique. So the last thing we needed to do was to create this feature right here. So what I did there was use a smaller end mill. I'm going to helically interpolate that hole. I could have drilled the hole first, I suppose, but that would have broken up the ID boring strategy. So this is the manner that I did it. Again, PartMaker has a lot of options when it comes to creating tool paths. So in this case, I'm just using a helix entry on the tool. So from there, we've got the part programmed. Now what we need to do is to generate the process table. And in the process table, we reorder the operations so that they can run smoothly at the machine. Right now, I have a fully processed process table. So let's generate the process table and see what we're looking at. What I've done is, whenever I can use the main and the sub spindles together in a synchronized mode, I've gathered the main spindle and the sub spindle processes that I can use together, and I've created a sync state for that. So I'm going to do the main face, then the ID work, and the first turn, the second turn, then the grooves, drill the sub side. This is the sub work. Notice that I've got the main turn work and then the sub work that I want to synchronize with the main work. They live together, okay? And then on the right side of the page, once I've ordered the operations the way I want to see them, I select our synchronizing button. Now, this is as simple as it gets for synchronization. You read what you need to do. We call this visual synchronization. If I'm machining with one tool on the main and I want the sub spindle to be synchronized to that, I machine with one tool on the main. I just look for the sub spindle mode and I look for machining with one tool on the sub. I place these together, select OK, and I have a sync state here. So I went through synchronizing all the main spindle and sub spindle work that I could. Then when I'm not using the sub spindle for machining tool paths, I'm going to use the sub spindle to support the part. So if I get aggressive with my milling, I'm not going to get a lot of chatter. I don't want to get a lot of harmonics on the tool. I want the tool to be able to create the feature without any deflection, that kind of thing. So I'm going to be using the sub spindle for a lot of my milling and drilling work just to support the part. And that's what we're doing here. From the third turn on, the drilling, the tabs, the holes, the front side slot, the fourth turn, the side flats, all the other work I need to do, I've got the sub spindle in what we call the follow support mode. So I'm having the sub spindle come up, grip on the part while I machine the rest of it, give me a more accurate tool path. And then I just put in the grip coordinate for the sub spindle and work my way through the rest of the part. Last but not least, the cutoff process, I'm putting that into a support mode as well. I'm cutting off, I'm moving the sub spindle up for the cutoff, and that prepares it for the sub side when we retract it for the synchronization to occur. Now we've got two methods for simulating the part. The first method is your basic simulation here, okay? The basic simulation just allows me to run through the part, and I'm moving awfully quickly here. I can slow that down if I need to. And now I'm in my support mode. And then you'll see the synchronized mode, tools working together until I need the sub spindle to support the part again. The other mode that we have is our full machine simulation. Load the post processor. You should be able to get to your machine sim. Open the machine file. In this case, I'm using a Sagami SS327 5-axis machine. Full machine sim, and here's the machine. Notice the tools are located in their respective holders. In PartMaker, what you do is you map the tools to the positions on the machine. Each tool that's being mapped is mapped to a specific area in the machine. So if I look at a tool, you'll notice that I've got this tool ID right here. This is an internal mechanism that tracks the tool and where it belongs on the machine. In this case, this tool is being used on the gang at station number 8. If I tried to use this tool for backside work or for sub spindle work, I would get an error stating that I'm using the wrong tool position. So these tool IDs map the tool to the machine. They're internal, you don't need to play around with them. Once I've got that mapped, I can come back to simulation. Here's my simulation options. I'm just going to slow down the simulation a little bit and run the full machine sim. You'll notice that I'm using the B axis for a lot of Z-oriented tools here. That's one of the nice features about this machine. You've got full B axis control. Here's the support mode. Side working tools. And then when we're done with the main side, the sub-spindle will move up for the cutoff, then it'll retract, and we'll do the synchronizing to finish the part off. Then we loop back into the support mode. And now we are in synchronized mode. We can also show the finished part. And here's our finished part. We do have features in simulation like compare to a solid model. So we can save this off as an STL file, then do a file compare, see if we're overcutting or undercutting, that kind of scenario. From there, we're going to create code. So I'm going to generate an NC program. These are my post options. If I've got a macro that uses a bar load feature, I can just put my macro number in here. When we recognize a remnant, we'll do the automatic bar feed. Wait queue commands, where do I want to start my wait queue commands? My machine options, air blast is a generic term for flushing the sub-spindle before pickoff. And cutoff detection here. We want to make sure that the cutoff blade is in the correct position before we open up the main spindle. We don't need to be shooting the bar through the machine. The phase angle here is just making sure that the main and sub-spindle C-axis angles are equal for pickoff, which is important if you're using hex stock, square stock, or if you've wired the sub-spindle collet to a specific shape for pickoff. We want to make sure those angles are equal for pickoff so that we actually pick the part off and not crash into it. This is our feed rate for the sub-spindle onto the part. If we're using a sub-spindle collet nose extension, we need to know how far that's sticking out of the sub so that we can truncate the pickoff position and select it in the right place. So if you're using extended nose collets, we take care of that as well. Then down here, stop to include user input. If the post processor prompts the programmer with questions, when we answer those questions, it'll flavor the code to what we need. So if I select OK here, I'm going to save the file. So here we have a question about the laser on the machine. Is your laser working diameter always the same as the stock diameter? If you say yes, then you won't have to worry about putting diameter values into the laser feature. If you say no, then it just means you're going to be working on different diameters with the laser on the part. Once I select OK, it's going to generate a file for me. I'm going to launch the NC program editor. Pick a machine. In this case, I'm just going to grab the Sagami. What do we got here? Okay. The reason I'm loading the machine in is so that I can align my weight codes. If my weight codes are lining up, then I know my synchronization process is correct. And I can just go down through the code, making sure that any weight state that I'm using is correct. Or just look at the code. Now here's our helical interpolation code. So that runs for a bit on its own. That's why you saw the code running by itself before we hit another weight state. But that's basically it. This is how you use Autodesk PartMaker SwissCAM to program your machines. Bring the model in, select your predefined construction planes to build the features around the part, generate your process table, reorder your processes, run your synchronization and your support functions, simulate, run code. Thanks for your time, gentlemen. I hope this has been a good video for you.